This is Unit 6, Video 6. In this video, we will be talking about the ideal gas law, probably the most famous equation in all of chemistry, if definitely the most famous as concerning gases. Now, previously we talked about the relationships between the four variables: pressure, volume, moles, and temperature. And Boyle's law, we said, related pressure and volume, and we said the pressure and volume were inversely related. So this is a proportionality symbol. So volume is proportional to the inverse of pressure. We also talked about Charles' law, which related volume and temperature. We said those two were directly related. And then Avogadro's law related volume and moles. They were also directly related. We also talked about Gay-Lussac's law, which related volume and, pressure and temperature. So we talked about that one as well. Now, if we combine all these together, we can actually symbolize it like so. We can say that volume is proportional to moles, that's from Avogadro's law, to temperature, that's from Charles' law, and inversely proportional to pressure, that's from Boyle's law. So we can put everything together into this big proportionality equation. Now, in order to make it into a true equation, the proportionality constant must become an equal sign. In order for that to be true, we have to put a constant in. Constants in equations serve to connect numerically, essentially, all the variables. So if we do that, and we call the constant r, just for fun, not k but r, we decided for some reason to use the letter r, then you get yourself this equation. Or if you rearrange it to where you move the p over to the v, you get yourself pb equals nRT. And this is the equation that you definitely want to memorize for this chapter and for from now on forevermore, really. And so there's actually license plates that drive around the country with this equation on it. Not too many of them, but there are a few. This is how important this equation is. And this is the equation we will be working with in this video and the next. Now, the constant is defined using different units. What you could do, in order to get the constant, you got this equation, PV equals nRT. What you could essentially do is solve for the constant, just plug a bunch of numbers in, measure a gas under a certain pressure, volume, moles, and temperature, and then rearrange the equation and solve for the constant R. And you can actually numerically determine what R is. Now, it will depend on what type of units you are using for your pressure, for your moles, for your volume, for your temperature. Moles will be the same unit, but all the rest of these units can actually have different, or all the rest of these variables can have different units. And depending on the units that you use, you'll get a different value. The most famous, the most common value to be used is this one right here, 0.08206. And the units here would be liters, atmospheres, moles, and Kelvin. All of these have moles, essentially. But if we use Kelvin, and all of these have temperature for Kelvin, you can't use Celsius or Fahrenheit since it's not an absolute scale. What then differs are the pressure and the volume. So this is the one we're going to use a lot. But there are a few more. If you decide to define volume in meters cubed, for example, and pressure in pascals, then you get yourself a different number. Now, this number right here is also important because it's the SI unit constant. So it uses all SI units, which means you're using the base units that were determined. For example, you're using kilograms, so pascals actually uses kilograms for mass, and meters and seconds for velocity. And then meters cubed would be the volume. So we'll actually use this one a little later on. This one will be a little less important. The more important one will be this guy here. So if you do decide to use 0.08206 for your R constant, make sure your pressure is always in ATM, make sure your volume is always in liters, and make sure your temperature is always in Kelvin. Alright, why don't we try a few problems. So here is a likely problem that we could do. What pressure is exerted by 0.325 moles of hydrogen gas in a 4.08 liter container at 35 degrees Celsius? We're asked for the pressure. Now, the original equation is PV equals nRT. So the pressure, rearranged for pressure, we'll just simply divide the pressure down here, and we get ourselves nRT constant. Let's go ahead and use the one that is the most commonly used, 0.08 to 06. And this has liters, atmospheres, moles, Kelvin for the unit. So we simply plug the numbers in. Now we have to make sure our units are matching the units of R. It looks like liters is good. It looks like moles is good. Temperature has to be converted to Kelvin. So let's do that. So remember that degrees Celsius to Kelvin. Kelvin is degrees Celsius plus 273. So essentially it's 35 plus 273, which should give us 308 Kelvin for our temperature. Okay, so all that's left to do is just plug and chug. So we got our moles, 0.325. I'll go ahead and put in the units. As you'll see, this will cancel, the units will cancel out. Our constant is 0.08 to 06. Now the units here are liters, atmospheres per mole Kelvin. And then finally our temperature is 308 Kelvin. All of this gets divided by our volume, which is 4.08 liters. Now go ahead and plug this in with me into a calculator. We got 0.325 times 0.08 to 06 times 308 divided by 4.08 for a total of 2.01. It looks like we have 3 sig figs all around, including temperature at 35 Celsius converted to 308 gives us 3 sig figs. When we're adding, we don't go by overall, we go by the decimal place, which is here. So that's correct. 201 should be the answer. What are the units? Well, we're measuring pressure, and pressure, if you've done it right, should be in atmospheres with the constant that we've chosen. So it should be atmospheres here. Now, you can actually see that the pressure comes out if you cancel everything else out. Moles actually cancel out. Liters cancel out. Kelvin cancels out. You are left with atmospheres, and that's the idea. And here is the answer. Our gas has a pressure of 2 atmospheres. So we've used the 3 known values to determine the unknown value. Let's do one more. How many grams of oxygen gas are there in a 2-liter bottle under Stp conditions? Now this is a fun little question. If you have a 2-liter bottle, say one of those 2-liter soda bottles, and it's empty, well, we'll say it's empty, but it's filled with air. We'll say all of it's oxygen. The question is, how much is in here? How many grams? Now that's a pretty fascinating question because we can actually determine the exact amount of grams in here using PV equals nRT. PV nRT is our big equation of the chapter. Alright, now what are we going to be solving for? Grams is related to moles, so we're going to be solving for moles. So rearranging the equation to solve for moles, we get moles equals PV over RT. We're essentially just moving the RT over down here, dividing it out. We have to make sure that our pressures match up. Now STP conditions, remember, stands for standard temperature and pressure, which gives us a temperature of 0 degrees Celsius, which is 273 Kelvin, and we'll have to use Kelvin for our temperature, so this is 273 Kelvin, and our pressure for STP is 1.0 atm. So these are our temperature and our pressure values. The R constant that we've been using, we'll use the same one. R will be 0.08 to 06 liters atmospheres per mole Kelvin. So it looks like we have 3 of the 4, because we also have 2 liters. Our volume is also 2 liters, so we can actually solve for moles. Let's go and plug the numbers in. Looks like we have 1 for the pressure, so we have 1.0 atm. Looks like we've got 2.0 liters for the volume. Our R, 0.08 to 06 liters atmospheres mole Kelvin. And finally, our temperature should be 273 Kelvin. Okay, go ahead and plug this in the calculator with me. It looks like we're going to be multiplying 1 times 2, which is 2, and we'll divide 2 by 0.08, 206, and then also divide it by 273. So 0.0893. We get 2 sig figs. Let's do one more just in case so we don't lose any significance. But in this case, we've got ourselves 0.0893 moles. Alright, we're almost there. It says how many grams of oxygen. Now we know oxygen exists in the air as a diatomic molecule, O2. So this is O2, moles of O2. We can go ahead and convert from moles to grams. A mole of oxygen is how many grams of oxygen? 32 grams of oxygen. So essentially we're multiplying that number by 32 to give us 2.8 or 2.9 to be precise, 2.9 in this case grams. And here it is. Now this is very important. What we've determined is how many grams of oxygen are sitting in a 2-liter bottle at Stp conditions. And this is pretty neat because we can go ahead and measure it, and sure enough, there'll be this much of oxygen in the container, as long as it's pure oxygen. If it's not, if it's air, we can actually do a similar calculation and determine air. Alright, so this completes video 6 of Unit 6. Oh yeah, try one of your own down below. Go ahead and try your own problem as a practice problem.